Here students, this is Prajesh Chaudhary Content Group. Let's see this very beautiful challenging problem of magnetism from Pathfinder. It's a build up your understanding question number 21. So let me read the question first. Question states a ring of radius r made of an insulating material has a mass m and carries a uniform charge. Initially it is at rest on a frictionless horizontal tabletop with its plane vertical. A uniform horizontal magnetic field of induction B pointing everywhere parallel to the axis of the ring is established in the region to the right of a vertical plane AA as shown in the figure. The ring is pushed forward to acquire a velocity V0 without any rotation. What should be the charge on the ring so that it starts rolling on the tabletop after completely entering the region of the magnetic field? Alright. So here is the situation. This is the region of uniform magnetic field B. It's a horizontal magnetic field towards me, perpendicular to the plane and towards the observer like me. And this is a horizontal surface tabletop, and this is a ring translating with velocity V0, non-conducting ring, radius r, uniformly distributed, mass m. Now it has entered somewhat into this region. The part of the ring that has entered into this magnetic field is subtending an angle 2 theta at the center. I am showing only this part. This is also theta. And it has entered a distance x, not fully, it has partially entered. So first of all, let me find this x. We'll use that letter. This is r, this is theta. So this distance would be r cos theta. This is r. So this is x is obviously r into 1 minus cos theta. Now the question is, in the question it is asked that what will be the charge of the ring so that when it fully is entered into the magnetic field region, it starts rolling without slipping. I mean the velocity and the angular velocity are perfectly matched. V is equal to r omega, like that. So when this has entered into this region, the velocity, initial velocity was V0, starting velocity was V0, and it did not have any rotation. There was no angular velocity, and because of the action of the magnetic force and torque, it has got, say, a new velocity. Say the velocity of center mass has now become V, and the angular velocity of this ring has become omega. This angular velocity has come because of some torque. We'll see later. So to find how this velocity and omega has come, we need to find the acceleration of the center mass and the angular acceleration. So for that, at this moment, I want to find what is the acceleration of the center of mass of the ring and the angular acceleration of this whole ring about the center mass. So what I am taking? I am taking this two element. This is a one element, this is another element, and these are on the same line. So I am showing only the upper part. So this is an element of that part which is inside the magnetic field. Suppose this element is subtending angle d phi at the center and its angular position is phi. So this element is between angular position phi to d phi, and this element is also between phi to d phi but below this line. So the charge of this element, the total charge is q. And the whole charge subtends angle 2 pi radian at the center. So the part which is subtending angle d phi at the center, the charge would be q divided by 2 pi into d phi. So the charge dq, this charge dq would be q by 2 pi into d phi. And now from the RBD, this is rolling. It has a velocity of the center mass and it has angular velocity. So with respect to center mass, it will have a velocity r omega, and in that r omega I have to add the velocity of the center mass. So this part, the velocity of this point would be, this is the velocity of the center mass, and with respect to center mass it will have a velocity r omega tangential, and this part will also be this velocity v, and with respect to center mass it will have a velocity r omega. Now for each part of this velocity I will write the magnetic force, that is a q v cross p. So b is towards me. So for this part v, the force would be v cross b if I do the right hand rule. So V cross B will come downward direction. V is here and B is here, V is here, B is here. So V cross B will come downward. So the force on this part is dq V cross V into B. And here also, because of this velocity, the magnetic force on this element will be dq into B. And similarly for this part, this r omega, q V cross B, because of this part the force would be towards the center, and on this part force would be towards center, and that would be dq r omega into B. Now see this force. Because of this force dq r omega B, there will not be any torque because this force is directly toward the center, and similarly for this part. But this will give rise to some force, net force. And because of this part dq Vb, there will not be any acceleration of the center mass because in the vertical direction, but it will give rise to torque because center is there, force is there, so it will try to rotate this in this sense. As you can see from the paper, that will be in the sense of the omega, and because this omega, because of that alpha, that omega has come. So let me first get the acceleration of the force center mass. For that we'll find the net force on the system of the ring. So the acceleration would be, because of these component dq r omega B, and one component would be here, and for this one component would be here, and these component, the vertical component would cancel, so there will be acceleration towards the left. So mass of this ring is m, so I will write the equation ma is equal to f net, and for f net, for these two parts together, for this part, okay, I can take this part. So for this part, the force dq r omega B, the component in this direction is responsible for the force. These component will get cancelled. The component in this direction would be dq r omega B into cos phi, and that is here, and minus sign because this is by the forward direction, right? So now put the value of dq here. dq is equal to q by 2 pi d phi r omega B, and here the only variable is phi because all these things I am calculated at this moment when this whole part is inside this. So here r omega B, these are constant, and so I have taken the constant thing outside the integration sign, and this is a cos phi d phi, and as I take this element from here to here, that will cover the whole part that is within the magnetic region. The limit of phi will go from minus theta to plus theta, so this integration would be 2 sine theta. Just simplify this. This integration will give me 2 sine theta, and this 2 and 2 will get cancelled and bring m to this side. So I got the acceleration of the center mass opposite to velocity, that is equal to minus q r omega B sine theta by pi m, right? And now I want to apply the torque equation. For this part, suppose due to this element the torque is d tau. So net torque will be integration of all this torque. So because of these two elements there would be torque. This element, this force, line of action of this force is at a distance. This is r, and this is phi, so this is r sine phi. So line of action of this force is at a distance of r cos phi from the point about which we want to find the torque. So torque because of this element would be dq Vb into r cos phi. So d tau is equal to, and because of that torque there will be alpha. So torque I will write I alpha. I about this point is a mr square, so this is mr square alpha, and this d tau, as I told you, because of this force dq Vb into r cos phi, that is fine. Again put the value of dq from here, q by 2 pi d phi, and all this q by 2 pi v b r take outside because all those are constant at this moment. Only variable is phi. So if I take the constant outside, this from dq q by 2 pi d phi, so I take q by 2 pi outside, here vbr I have taken outside. Inside what I've got? Cos phi d phi, and again I will, as I take this element from here to here, the whole part of the ring that is within the magnetic field will be covered. So once again this integration will become 2 sine theta, and this 2 and 2 will cancel, so the integration will give from here mr square alpha, and this is a qvb r sine theta by pi. So just rearrange here, so I'll get alpha is equal to qvb sine theta divided by pi mr. So that's what I've got. Now let's go to next page. So whatever we got, just we want to manipulate these things. So a we got this and alpha we got this. Let's divide these two. So divide these two. A by alpha, you see that q b sine theta and pi m will get cancelled. So if I divide these two, I will get a by alpha is equal to minus r square omega by v. Alright. So that will get. So just rearrange that. So that let me take v here and alpha here. So v into a is equal to minus r square omega alpha. And now what I want to write? I want to write this a as a dv by dt. A as a dv by dt and alpha as a d omega by dt. And just cut these dt. So what you will get? You will get v dv is equal to minus r square omega d omega. And the limit. When it was outside the magnetic field, the velocity of the center mass was v0, and at that moment angular velocity was 0. And now that it has entered distance x inside, and the part of the ring that is within the magnetic region is subtending angle 2 theta at the center, at that moment the velocity of the center mass is v and angular velocity is omega. So integrate this integration will give you v square by 2, and this integration will give you omega square by 2, and put the limits. So you will get v square minus v0 square by 2 is equal to minus r square omega square by 2. This 2 and 2 will get cancelled, and rearrange this. So rearrange that, will get r omega is equal to square root of v0 square minus v square. This is another relation. So now let's go to next page again. So we got this thing, r omega is equal to square root of v square minus v0 square minus v square. v0 was the velocity of the center mass when it was outside the magnetic region, and the v is the velocity of center mass when it has entered a distance x inside, and at that moment angular velocity is omega. So now it is getting entered into the system. Now this is the moment when it has a fully entered into this magnetic region. This is the first moment when it has fully entered. At this moment, suppose the velocity of the center mass has become Vf and the angular velocity has become omega f. And now the pure rolling has started. That's what the condition is given. So at this moment, Vf will be r omega f. Vf is equal to r omega f. And from here to here, all this moment, this equation is satisfied. So satisfy this equation for this moment also. So just square this, r square omega square is equal to v naught square minus v square. So for this moment, v is equal to vf and omega is equal to omega f. I put it here. So I will get r square omega f square is equal to v naught square minus vf square. And when it has started pure rolling, so this will be vf square. So vf square is equal to v naught square minus vf square. So that will, let me take it here. So that will be 2 vf square is equal to v naught square. So vf will be v naught by root 2. So one important thing is that when it has entered fully inside the magnetic field, the velocity of the center mass decreased because the acceleration was opposite and it has become v naught by root 2. V naught was the starting velocity. Now the last thing that we've got. So now once again let's go here. So this is again the general situation. Already it has entered distance x. R omega at a general moment at this moment was r omega was v naught square minus v square square root. X we had written in the beginning. Once again you can see this is r, this is theta, so this will be r cos theta. So x is equal to r1 minus cos theta. I will be needing dx. From here if I write dx, that will be r sin theta d theta, and acceleration was this, a is equal to minus q r omega b sin theta by pi. Velocity of the center mass is v. It has displaced within the magnetic region at distance x. So I can write A is equal to v dv by dx. So A is equal to v dv by dx. Now some rearrangements are needed. So what I want to take, this r omega, I want to bring it here, and dx I want to take it here. So let me take it here. This r omega as a whole, r omega here, and that r omega I will bring here. So that will become how much? V dv. This r omega, that r omega is square root of v naught square minus v square. That has come here, and this is minus qb sine theta by pi m and dx. And this dx I will write r sine theta d theta. Alright. So this thing I will get. So v dv square divided by square root of v naught square minus v square is equal to minus qrb sine square theta by pi m d theta. And now just we have to integrate it from the beginning till it just enters to the magnetic region. So that was now the whole summary. This was the beginning. It was sliding, it was translating with the center mass and velocity v naught, and this is the moment it has entered a distance x inside. For this moment we have this equation, and at this moment this ring is, the part of the ring is subtending angle 2 theta at the center, and this is the moment it has fully entered into the magnetic field region. So I am here in this equation, I am using only the linear motion. For the linear motion, when it was just outside, the velocity, this v was v naught, and when it has fully entered into this region, the velocity was v naught by root 2. When it was totally outside, this theta was 0, and when it has a fully entered into the system, the theta has become pi. So now integrate with the suitable limit from v is equal to initial value v naught to v naught by root 2 and theta from 0 to pi. So this is the limits. For this thing, this is a simple integration. I am writing directly, but I can give you hint. For this thing, what you can take this whole thing as a t. Make a substitution, this whole thing as a t. So if you take this whole thing as a t, so that whole thing will become dt. This whole thing will become dt. So this dt integration would t. So this integration you will get basically square root of v naught square minus v square. That is what you will get. And for this integration, that is simple thing. Directly what you can do, average value of sine square theta from 0 to pi is 1 by 2. So the integration would be the average value into the interval. So average value is 1 by 2 and interval is pi minus 0, that is pi. So this integration would be a pi by 2. So just put those things limit and integrate it. So eventually just simplify, you will eventually get the q is equal to root 2 m v naught divided by rb. That would be our answer. Thank you.